Okay, good morning. It's okay. So it's a pleasure to introduce Pavel today. Well, he was explaining this morning. He was telling me his life, and in fact, I find that Pavel as an astronomer is quite peculiar in a sense. Not because the dark matter and others, of course, forget about that. But because normally astronomers, we do live in a place, and then when we finish our, the degree and the PhD and so on, we start to travel around the world, okay? So in Pavel's case, it's the other way around, okay? So he was a true refugee from the Czechia, okay? Well, now, Czechoslovakia, okay? In '68, I went to Germany when he was a kid, and then South Africa for 5 years, living there as a child, okay? And then come back to Germany, and this has nothing to do with astronomy; it's just life, okay? And then Australia. Australia, and the physics degree, and then the PhD in Cambridge, and then he went to Germany as a postdoc and stayed there. Okay. So since then, and he just until when you was a director of the Arglande Institute in Bonn.
Oh God, was it 2013, 2014?
So you luckily now are free.
Yes, yes.
Okay.
So, very much so, yes.
Okay. So regarding the science, well, I do not know what to say. I mean, everybody, we are talking about Kroupa, IGIMF, Kroupa. So the issue is that it took a while, as everybody knows, to settle a sort of trustable IGIMF since the time of Salpeter, okay? So and Pavel fixed it, and then became this famous, of course, that we are every day mentioning the Kroupa IGIMF, we would say. And it took a while to him, a lot of work to do it, and settle it, and now it seems that Pavel, maybe he doesn't like his own IGIMF, okay? So he's moving to a new theory, which is the integrated galactic IGIMF, which there is a room for the IGIMF to vary. So he doesn't like it anymore. So well, I don't want to say. So Pavel.
Thank you so much. Yes. Yes. So I'm here now primarily because of the really rather spectacular and amazing work which Alejandro Vazdeikis and his team have been doing on the IGIMF in elliptical galaxies. So elliptical galaxies I have not actually been looking at myself because they are a different type of object than the majority of galaxies which are star forming. So ellipticals are essentially fossils from a very early phase of the universe, and what I want to now learn is how can we apply what we see in the Milky Way in terms of the star formation process, as well as in the local group and maybe the local universe, to elliptical galaxies. Can one actually understand the process of elliptical galaxies in terms of the IGIMF and its time evolution in terms of what we see actually locally? So this is what I'm very interested in. That's why I'm here to actually learn from Vazdeikis. Perhaps this is one of the best places to actually do this, since I think there's no other group which has been so active for such a long time on actually studying the details of elliptical galaxies. So today, however, I will be talking about what we know about the IGIMF from my point of view in star-forming systems, and then with time I hope to connect with the elliptical galaxies, but not in this talk yet because we are not there yet. The IGIMF has been often taken to be a probability density distribution function, but lately I think it seems to be actually something different, and I want to explain to you what I mean with this. So coming back to a little bit more to the definitions, we know that the IGIMF is the number of stars in a small mass interval, and After detailed star count analysis, there's a sequence of papers with this group here, and summarized in a review recently. One can write down from what all the from the distribution of stars in the Milky Way disk, in the bulge, in the dwarf satellite galaxies, as well as in actual star-forming regions in the Milky Way and the large and small imaginary clouds, that the IMF is fairly nicely representable everywhere as a parent distribution function as a two-part parallel. So basically this is the salpeter part above 0.5 solar masses, and then below that there seems to be a flattening to the slope of about 1.3 if salpeter is 2.3 here. One can also represent it as a log normal, so this is not a Chabrier form. Basically, one still has to use the Chabrier, the salpeter, so Pauli slope with the salpeter value above about 1 solar mass, and then glue a log normal onto this, which is mathematically nasty compared to the simple two-part Pauli form, which is why I always use the two-part Pauli form, because it's much, much easier to work with. Doing integrals and so on with this form is simply unattractive. Here's a plot of this. There's a number of stars against mass. So the two-part Pauli form is just this red line, and the best representation in terms of log normal here in this part is shown as this dashed line. So that's what we can consider to be the hypothesis, that this is the parent distribution function from which stars are drawn when a star formation event happens. One question one can ask is this true everywhere? And if you take a whole galaxy, is that still the distribution we should be using to describe a whole galaxy? And that, of course, has deep implications not only for cosmology, but also for understanding the origin of matter as such. Typically what we undertake is that the IMF, we assume that the IMF is a scale invariant probability density distribution function. That's actually quite a strong assumption, which is very, very popular. And it actually has the following implication, going back to something which Kennicott has formulated in 1994, the star formation relation. If we observe an H alpha flux from a galaxy, then we can calculate the star formation rate in the galaxy with this type of equation, which means the star formation rate is always proportional to the luminosity in H alpha for all galaxies. And that's simply because if the IMF is a scale-free parent distribution function, probability density distribution function, a higher star formation rate just means you're making more stars with more H alpha photons coming from the massive stars, indirectly, of course. And this can be calculated given the IMF, how many ionizing photons come from the stars in total in a population with a given IMF. So this is a strong implication. And that's how the star formation processes and how the matter cycle in galaxies is interpreted today. So you look at a dwarf galaxy with a low H alpha luminosity, one calculates the star formation rate based on that equation. And if you look at a major galaxy with an H alpha flux, you calculate the star formation rate from that, and then you find certain correlations, and then there's a huge population of theorists trying to understand these correlations which come out of such work. Yeah. So the IMF is indeed the key to understanding the matter cycle in the universe, because if we know how dwarf galaxies are forming stars inefficiently based on the Kennicott relation, as opposed to massive galaxies which are supposedly forming their stars efficiently, then this implies a gas consumption time scale in the various systems, which also implies that these galaxies have to be accreting gas, and this therefore touches on the matter cycle of the universe, which then has to be understood. So the IMF has a scale invariant probability density distribution function. It means that we have stochastic sampled stellar populations when discretized. This means, for example, if this is the number of stars as a function of mass, and this is the parent distribution function, the invariant distribution function, then we make one cluster, one event of 150 solar masses, and this would be the actual distribution of stars drawn from such a distribution in one particular taking. Yeah? So you can see the implication of this is that there is noise, of course, because it's a stochastic process, and the actual, if you now fit the slope to this function here and there, you get a different slope to the actual parent function, which means there's a natural stochastically sampling the IMF means that the resulting populations which you create from this will have variations in the slopes, just because of statistical fluctuations. So stochastic variations in the shape of the IMF from case to case. And there's been some discussion on this some time ago, by various people. Also it means, and this is typically done in galaxy simulations, that one assumes that there are fractions of stars in low mass galaxies. So a little dwarf galaxy with a very low star formation rate is making 1/10 of a supernova, for example. This is typically done in cosmological simulations, which of course is physically wrong, because a dwarf galaxy with such a low star formation would not make 1/10 of a supernova. It would simply not make a supernova. Yeah. So it tests then, is this, so the hypothesis is the IMF a probability density distribution function? And the question is, can we want to test this hypothesis, and can one discard it or not discard this hypothesis? Okay, so is the standard assumption invariant probabilistic IMF consistent with observations? And actually we can now see that there is an upper mass limit of stars. We see that just by pure observation, systems which have formed stars do not seem to make stars which are much more massive than 150 solar masses. Although there are a few cases where they seem to have very massive stars. These can be nicely understood through the dynamical processes in dense clusters where the stars merge. Yeah, so we can do these calculations and show that these particular very rare cases actually must occur if this is true. So this has been shown by a number of authors that there seems to be a physical constraint on the IMF. Therefore, this is already not true, because if anything, it's a constraint probability distribution function, because there's a constraint that means that stars more massive than about 150 solar masses can't form for whatever reason. Then we can look at the observed variations of IMF shapes, which actually turn out to be much smaller than in theory. So this is the argument. Here we are, so this is the mass functions of Paolo, and alpha is the number of alpha values is plotted here as a function of alpha. So we look at, say, 100 OB associations and star clusters, and in each one we construct a mass function fit alpha, and that value, we make a histogram of those values. So this is here the histogram of the observed alpha distribution, which you can see very beautifully peaks at the salpeter value of 2.3. And the data which go into this here are from OB associations and young star clusters in the Milky Way, large Magellanic Cloud and small Magellanic Cloud. So quite a large sample from many different authors, many different telescopes and many different authors. And if you do this histogram, then that's the distribution. If we now make a model where we take where we repeat this with these OB associations, but we assume there's an IMF, and we take randomly stars from this and measure the slope from this, and then look at the distribution of these alpha values, we get such a distribution, which is very different. Okay, so this is the actual theoretical distribution from the simple experiment, and this green histogram is the data from these observations. And the remarkable result from this is the following, that there are no asymmetries and sharp salpeter massy peak in the data. It is incredibly sharp. Yeah, this dispersion here is incredibly small. Furthermore, it's totally symmetric. You see these wings in the distribution are symmetric about salpeter. It's not like there's a skewing to one side or the other. And the model is worse than the data, which means the model, although the model has no observational uncertainties, it has a wider distribution than the observational determined slopes of the IMF, which have observational uncertainties. Yeah, so that's really remarkable, which I think actually shows that nature is not stochastic. A long time I've been interpreting this to be a sociological bias. I was telling myself the observers are always, they want to find salpeter, and they find salpeter. Implication of this is that one can't trust observers. So I think this is not a favorable interpretation. And actually I think, and this is the nice thing now, that given all the other evidence, the actual interpretation here is that nature is much, much more self-regulated and organized than it being stochastic. Okay, so that's one indication. So confirmation bias, a sociological bias, is one possibility, or real young populations are not stochastic ensembles from the IMF. So observed systematic change of galaxy-wide IMFs with star formation. So if the IMF were a scale invariant probability density distribution function, it would not be varying in massive galaxies as opposed to dwarf galaxies. What is observed is exactly the contrary. There's this remarkable paper by Gunawardhana et al. It's an Australian group, and they looked at thousands of star-forming galaxies, and they studied using H-alpha and a broadband color the ratio of massive stars to somewhat lower mass stars. and the systematic change of this ratio as a function of the star formation rate of the galaxy. They are the first ones to actually do this in terms of the star formation rates. So they find a strong IMF star formation rate dependency is discovered, which shows that the highly star-forming galaxies form proportionally more massive stars. They have IMFs with flatter Pauli slopes. So this is the plot. Here is the alpha value as a function of the star formation rate. This is again a reminder of the IMF. So this is up here saltpeter slope. So the canonical invariant IMF would be here. And these are averages of these galaxies as a function of star formation rate. And for whichever model they look at, because they look at all the various possible biases like photon leakage, dust obscuration, reddening, and then they do different models, inclination, corrections. And in every single particular parameterization, they find there's a systematic change that IMFs with a high star formation rates, in galaxies with high star formation rates, are top heavy, and galaxies with a lower star formation rate are typically more like saltpeter or more like the Milky Way up here. So this is the Milky Way is at a star formation rate around this region here. And this is confirming, and it's an update on these previous independent studies which have already shown exactly this result. So it's a very robust result by various research teams working in competition with each other, finding such a typical trend, which clearly shows that the IMF is not a probability density distribution function which is invariant. So previously noted evidence for top-heavy IMF was that in star-bursting regions, the luminosity was often understood to be too large for the amount of gas mass to sustain the burst unless the IMF is top-heavy. The stellar counts of cosmic star formation history implies too many low-mass stars locally unless IMF was top-heavy at large redshift when star formations were high. Basically, you can say if the IMF was invariant, at a redshift of 2, there was a maximum in the star formation rates. And if we now calculate how many low-mass stars should be locally, given the higher star formation rate, we would have far too many low-mass stars, which means at the higher redshift, when the star formation is higher, the IMF must have been top-heavy, otherwise we would observe far too many low-mass stars. That's an interesting argument. And then there's the high rate of Type 2 supernova in the starburst galaxy ARP 220, which suggests again a top-heavy IMF in that system. I think there's something like 10 supernova per year going off, which can really only be explained given the morphology and the mass in these systems, only be understood if there's a top-heavy IMF. And since recently also deduced from globular clusters on UCDs, which I'll mention briefly later. And there's a literature which discusses these sort of issues. And then the concept of star formation being stochastic is ruled out with M33, I think in a very nice and elegant argument, because we can say that if star formation is stochastic, as many people believe, then you would be able to form massive stars and stars anywhere at any time, sort of stochastically, basically, in the model. Is this true? Well, this is actually ruled out, because we've looked at this in terms of the star cluster distribution. So this paper, the galactocentric radius-dependent upper mass limit of young star clusters, rules out stochastic star formation. So we find that the masses of the most massive young star clusters in M33 decrease with increasing galactocentric radius, in contradiction to the expectation from a model of randomly sampled star clusters. So we have ruled out with extremely high significance that this is the result of size of sample effect. So the idea here is that the result of this is that if you look at the galaxy, we look at radial annuli, and we look at the most massive second, third, and fourth most massive clusters as a function of radius. And if the process is stochastic, you would have the equal chance of forming a massive cluster outside as inside, more inside the galaxy, subject, of course, to your Poisson noise. So we did this exercise, and this hypothesis entirely ruled out. What we see is that the most massive clusters, they follow the gas density of the galaxy, which means that the IMF is, so the process of star formation is not stochastic, but it's actually subject to local conditions. Of course, this is intuitively clear. You can't make a very massive cluster at a point where you don't have as much gas. However, in terms of the modeling, this has been ignored, this very simple notion. And this is a very beautiful argument against stochastic star formation. There's a lack of O stars in this region. So what you see here is an image on the sky of the Orion star forming region. These are the north clouds, this is the south cloud. The Orion Nebula cluster, trapezium cluster, is just here. And these red dots are stars found with the Spitzer telescope. And so the Spitzer discovered that there's this what is referred to the distributed star formation in the southern part of this L1641 cloud, which until then was not known to actually make stars. There was at least it was not known that there were so many stars being formed in this region. The ONC, of course, was well known, and these 4 embedded clusters here were also well known from the work of Elizabeth Lada. And now the remarkable discovery here is that if you cut this here, down here you have a few thousand stars which are formed, and not a single O star. And up here you have a few thousand stars being formed with quite a few O stars. Okay, so in this very impressive paper by Sue Hartmann et al. 2012 and 2013, they show that there's a deficit of massive stars in this region, which very clearly shows that the stochastic IMF in each group is ruled out. You see the star formation is in all these little groups. It's not actually distributed. It's actually confined to embedded little clusters, but each embedded cluster is not making a massive star. Okay, so if you take, so from the number of stars down here, you would have an equal chance to have as many O stars as in the population up there if star formation was stochastic, and this is ruled out because we see that in this region here where we are forming only low mass embedded clusters, massive stars are not forming, although the total number of stars is the same as up here where there's one fairly massive and dense cluster. Okay, so many small low mass groups down here do not yield the same IMF as one massive cluster up here. If you add all of these together, you will not get the same IMF as up here. So there are these 5 arguments, and these 5 together show that real young populations are not stochastic ensembles from invariant distribution functions. Okay. So the IMF cluster mass function as an invariant probability density distribution function, I think, has to be discarded. Yeah, this is at least my conclusion given the data. I would not be able to work with this hypothesis anymore given the evidence. So then the IMF as an optimally sampled probability density distribution function. If it is not a probability density distribution function, it is something else. What is that? It took me some time actually to invent something new. Maybe for the mathematicians this is already extremely well known. I don't know, but it took me a long time to even formulate the concepts. How do you work with a distribution function which is not a probability density distribution function? Yeah? And actually I came up with this. I call this the optimally sampled probability density distribution function. Or you could just say an optimally sampled distribution function, optimal distribution function. What is an optimally sampled distribution function? Basically, given a mass reservoir in stellar mass, for example 1000 solar masses, that's your little cluster, starting with the most massive star, select the next massive star such that this MECL mass is distributed over the distribution function without Poisson scatter. Yeah? So that's a nice mathematical challenge. It's actually absolutely trivial to do this, but when you don't even know how to formulate the question, you wouldn't believe how hard it is to actually even come to this conclusion. And that's very simple. So that's the formulation in the simplest form. We now have a much improved version in a paper by Christine Schulz et al. And so what you do is you solve this little equation. Right? There are these 2 conditions. So this is the mass of your system, like 1000 solar masses, is the integral over all your stars in this little cluster, given the distribution function. And then there's one star between the most massive and the physical limit. So this is 150 solar masses up here. If you solve this, you get the first most massive star, this one here. And then you can calculate the second most massive star with this little equation. Basically, it just means that given your mass, you know at which point your next star is in the sequence to actually then fully sample your distribution function. So with this little the description, one can optimally sample any distribution function. This is now the example. So here we have number of stars against mass. Here is the canonical parent distribution function, the 2-part Paolo form here. Again, this is 150 solar mass case. Remember, this was the stochastic sample, one particular rendition, which we had before. And this is the same cluster with 150 solar masses, but now optimally sampled. You see, there's absolutely no Poisson uncertainty, no Poisson scatter. We have a perfect representation in terms of a discrete sequence of stellar masses of the distribution function. So that's a mathematical model. It's an extreme where we would say star formation is completely, perfectly self-regulated. I don't think nature is actually as perfectly self-regulated as that. It's a mathematical model we can work with. as opposed to the other extreme case where we talk about a completely stochastically sampled distribution function. So the IMF has an optimally sampled distribution function. So the Orion case suggests that the most massive star may depend on cluster mass. Remember, the south cloud is making many low mass clusters but no massive stars. So from above we can consider that each correlated star formation event, which is just an embedded cluster, there's one most massive star. And these are the two equations I had before. There's one star between the M max and the 150 solar masses. And the mass of the population is given by this integral. So we just have to solve these two equations to get a M max MECL relation. So this is just a mathematical exercise currently. We can solve these equations and then we get this. So basically what it means is if you have here the number of stars as a function of mass, in Taurus Auriga star formation you have this distribution function. It's the same in shape, canonical distribution, but if it's optimally sampled, the most massive star turns out to be about 2 solar masses. In the Orion Nebula cluster, again, the same distribution function. If it's optimally sampled, the most massive star then is about 50 solar masses. And in something like R136, the starburst cluster in Large Magic Cloud, if it's optimally sampled, but because of this physical limit of about 150 solar masses, it will be the most massive star here. Yeah? So that's what this means. And now we can solve these two equations. We then get this plot. So this is M max. This M max here is here. This is the mass of the cluster, embedded cluster in stars, like 1,000 solar masses. And these curves are solutions to these equations, assuming the physical limit is 150 solar masses in this equation or 300 solar masses in this equation here. We have these two curves. So now what do the observational data tell us? This is just a mathematical model, as I was saying. There's some physics behind it, as I said, in the sense of very self-regulated star formation principle. And these are the data. So each point is an embedded cluster, very young, where we have an estimate of the mass of the cluster and the most massive star. The uncertainties are large on each point. That's how they scatter. Remarkable is the small scatter down here. These are data from Kirk and Meyers, and these here are data from various sources collated by Carsten Weidner. And the remarkable result from this, and this is truly remarkable, is that each point has large uncertainties. Many of these come from different observing teams, from different using different observational technologies, and the scatter here is too small to be consistent with randomly sampling from the IMF. So if we have randomly sampling from the IMF, you would expect 2/3 of all points to lie between these two dashed lines here. What we see is that far more lie in this sort of region. I mean, there's some indication of systematic deviations from this curve, but the scatter is too small to be consistent with random sampling. The dispersion of that is highly inconsistent with random stochastic sampling from the IMF, because the large uncertainties would imply this to be even a wider distribution than pure stochastic sampling. And what we actually see is, despite the large uncertainties, the scatter is actually smaller than stochastically sampling. Okay, so important, the scatter in the data is mostly due to being from measurement uncertainties. It is intrinsic scatter may be very small. We have a little project now in Bonn where we are trying to calculate away the scatter through uncertainties, observational uncertainties, and it would then look something like this, which means there's an incredible self-organization in star formation. When a molecular cloud core starts making a cluster, the self-regulation which goes on in this, as the stars are appearing and feedbacking, so earth flows and the radiation from the forming stars seems to limit the final mass in stars which comes out of it, and the rest of the gas is dispersed. This is what this must be implying. Okay, so so a result, the scatter in the data is mostly due to being from measurement uncertainties, i.e. intrinsic scatter may be very small, and the IMF can only be a probability distribution function if sampling from it is close to optimal. So that's a result just only from this particular analysis exercise. And so the IMF is an optimally sampled density distribution function, and by implication star formation is largely self-regulated. So self-regulation seems to be an incredibly important physical process in star formation. In fact, star formation seems to be is essentially a self-regulated process. Gravity begins the process. Everything beyond that is self-regulation. This seems to be what is coming out of this sort of analysis. So if you now look at these embedded clusters, and we call them now CSFEs because there's a particular subgroup of astronomers who started saying that stars typically do not form in embedded clusters, but of course they form in correlated structures because they form in the density peaks of molecular clouds, so they must be forming correlated star formation events, and technically they are embedded clusters. Still, so these CSFEs, what do we know about them? We can construct models of the stellar dynamics of these systems. The Plummer model is the simplest solution to the collisionist-Boltzmann equation, which exists. We know that nature seems to like that particular solution. Globular clusters are quite well represented by that, and the filaments in star-forming clouds, the cross-sections are also Plummer-like. So this is the fraction of stars within a certain radius given a Plummer model. So for example, at 2 Plummer radii we have 20% of the stars being outside of 2 Plummer radii, and so this implies that in any such correlated star formation event, if you model it as a Plummer model, then if you'd say that beyond 3 Plummer radii you can talk of isolated star formation because you might have stars somewhere here. Mathematically they belong to the structure. An observer would declare these as isolated star formation. Okay, but actually mathematically they are belonging to this model. Furthermore, these structures here are dynamically very active. They are dynamically active and leads to rapid dispersal of additional stars which may appear to have formed in isolation. So these central regions shoot out stars drift out, they are actually expelled, and so at any point immediately after star formation starts, you already see stars around the structure. So we can, as an observer, very quickly very easily misinterpret what you see as evidence for isolated massive isolated star formation. So assuming star formation takes place in these correlated star formation events, the stellar population from an ensemble of these can be computed if the distribution of these is known. So the idea is we have a galaxy and we have all these embedded clusters or correlated star formations forming, and we know that the distribution function of these is about a power law with beta about 2 from Ladd and many other works. So the distribution of embedded clusters is again a power law. Now, before I continue to make a whole galaxy, there's some intriguing evidence that the IGIMF actually, in individual CSFEs, embedded clusters, changes its shape. The evidence is most remarkable, I think. We look at a case like R136. This is the local starburst cluster in the local group, the most massive object. It has a dimension of about 1 or 2 parsecs and has a mass of about 100,000 solar masses. It's something like a tiny little globular cluster. It's extremely young, 1 to 2 million years possibly. What do we know about this? So what we did is we made n-body models of this system and calculated how many stars are ejected. And this has implications for the IGIMF as follows. We find that if this is the stellar mass, so this is 150 solar masses, 100 solar masses, 10 solar masses, the ejection fraction rises up. So the more massive stars are preferentially ejected from the cluster as opposed to the less massive stars, because the massive stars, when they interact, they have a lot of binding energy, they can really kick each other out. If we then take these calculations, so we know which fraction of massive stars of which mass are ejected by the age of the cluster, we can correct for this statistically. So we have the observed mass function, the number of stars against mass. This is the observed mass function, which is observed to be about salpeter. And if we now, and this is the current IGIMF deduced from the stellar content in the cluster, if we add back all the stars which must have been ejected from the cluster, if we add it back in, we find that it must have been somewhat top heavy. Yeah, because you have to add back all the stars which have been ejected, and then it becomes top heavy. And these are the various, because we don't, there's a scatter, and so we can do various fits to these curves here, to these data, and so whatever correction we take, it could be a little bit top heavy, a little bit more top heavy, but the point is that whatever you do, because R136 is expelling massive stars, it must have an IGIMF which must have been more top heavy than the observers tell us, because they don't see the stars which are outside, which have been ejected. So that's quite nice evidence. From theory, we know that it must be getting top heavy, because this is work from Sami Dip. So this is the pre-stellar core mass function. This is the function, the distribution of cores which are making stars in a cluster. And he's calculating how this distribution is changing as a function of time. You see this is in free-fall time, so there's extremely short time scales. 0.07 free-fall time. The free-fall time of this entire object might be something like 500,000 or 1,000,000 years. So these are very short times. What's happening is as this cluster, this model, this gas system is collapsing or contracting, individual cores appear which are making stars, but before they make stars, they can coalesce. And if the density is very high, they coalesce very much. And so you can see that because of this coalescence, the top end builds up with time towards a top-heavy form before they make stars, and then these cores make stars, and they will make massive stars, while these make the less massive stars. So that's quite intuitive and nicely understandable. But then there's some very nice other evidence for the IMF actually becoming top-heavy in starburst regions. In globular clusters, there's a deficit of low-mass stars which increases with decreasing concentration. So this is the work of Demaci et al., a remarkable breakthrough paper where they, for the first time, found that if you look at globular clusters with a low concentration, the low concentration clusters are missing low mass stars, while the high concentration clusters have a fairly normal mass function. And the stellar dynamical evolution of such clusters give us exactly the opposite trend. Globular clusters with a high concentration should be deficient in low mass stars because the dynamical clock is ticking faster and they evaporate the low mass stars, while the clusters with a low concentration, the less dense clusters, the clock is slower and they don't evaporate the low mass stars. And this is very well confirmed by n-body models of clusters in tidal fields orbiting in galaxies. So this, what is discovered, is exactly the wrong way around. And so what we find is that the only way to explain this Demaci correlation, as we call it, is to say that the clusters formed all very compact and mass segregated, and then the massive stars expelled the residual gas, the clusters expanded, and lost low mass stars across the tidal boundary at the time when the galaxy was just building up. So the tidal field at that time was very fluctuating. Some clusters were in a strong tidal field, some clusters were more isolated, and the clusters in strong tidal fields lost the low mass stars as the cluster expanded because of the energy input from the massive stars which drove out the gas. And with this we have a handle on the energy we need for each individual cluster to actually do this damage to the cluster. And with that we can calculate how many massive stars most likely were in these individual clusters. And with this calculation we find remarkable correlations between the initial density of the clusters and the metallicity of the clusters. And this leads to a result published in this paper that typically the globular clusters which had a lower metallicity had a top-heavy IMF, and those clusters with a higher density also had a top-heavy IMF. I'll show the correlations a bit later. Independent of this argument, completely independent of this argument, we looked at ultra-compact dwarf galaxies which have a higher dynamical mass to light ratio. So ultra-compact dwarf galaxies are like globular clusters except that they are up to 2 orders of times more massive, so up to 100 million solar masses, and somewhat bigger, but still extremely compact. And this can be nicely understood. It cannot be understood with dark matter because the phase space constraints are too severe. But it must most likely, it can be explained with top-heavy IMF in the sense that these dynamic mass to light ratios come from neutron stars and black holes in these systems. So by looking at the ultra-compact dwarf galaxy as a function of mass and calculating the mass to light ratio, we know how many remnants we have to put in there, and with that we get a constraint on the top end of the IMF because we know how many remnants, neutron stars and black holes have to be in there. And with that we can actually calculate how the IMF depends on density of the UCDs when the UCDs were young. So this and that are independent arguments. And then we have another one saying, look at the X-ray sources from these ultra-compact dwarf galaxies. What we say is that the UCDs have an overabundance of low-mass X-ray binary sources, which can be explained by them having a surplus of black holes and neutron stars. Again, by looking at how the correlation of the LMXB fraction as a function of mass changes, we calculate how the IMF changes with the density of the UCD. So we have this so we then have a solution given the X-ray sources. We have a solution given the mass to light ratios. These two are entirely independent data sets and arguments. And we have a solution from globular clusters. And what this implies, and the remarkable thing is that all three agree. This is the truly amazing thing, because the argument has not been engineered to agree, it just comes out to agree. Yeah? Otherwise I wouldn't be explaining this. And so what we have here is the IMF, the number of stars function of mass, and as the density increases we are seeing that it becomes more and more top heavy, and the brown dwarfs are a separate issue. So this is work done by Jörg Dabringhausen, who's now in Concepción in Chile. It's a postdoc, and so we have these correlations. This is the salpeter slope alpha at 2.3. These are individual clusters. Here, for example, R136, Westerlund 1, Arches cluster, are these open symbols, and the 3603 starburst cluster. And as we now go up in cloud density, we find this correlation. So each open circle is an individual global cluster, which we could calculate backwards in time to its initial configuration, given its current state. Yeah, and you see how amazing this correlation is. And these are the results from the ultra-compact dwarf galaxies. So we have a correlation that above this value, we have an IMF which we can describe with this functional form as it becoming top-heavy with increasing density. Above a star formation rate density of about 0.1 solar masses per cubic parsec per year, we have evidence for top-heavy IMF. Below that, it seems to be invariant. We do the same with metallicity, because each individual globular cluster has a metallicity measurement. And so this is again the salpeter canonical slope here, where this is now the metallicity, and we can nicely see how, again, the mass function becomes top-heavy with decreasing metallicity. This just comes out of this analysis. It's not put in. From my point of view, this is the first time we actually see evidence how the IMF actually changes with metallicity, as has been expected since many, many years from theory, from elementary arguments in theory. So we can then put this together in equations. So alpha 3 is equal to salpeter, so above 1 solar mass, if this parameter x has this value, and it then becomes top heavy according to this equation, if this value is larger than this value, and x depends on the metallicity and the density. Furthermore, at the low mass end, some time ago I already noticed that there might be a trend looking at the local star cluster like Pleiades, Hyades. The thick disk mass function has been confirmed, the global the bulge mass function of stars, and some globular clusters, that there might be evidence for a trend that the IMF becomes increasingly bottom heavy with increasing metallicity. So this is published in this paper here. And the canonical values here are 1.3 for the low mass stars and 2.3 for the stars above 0.5 solar masses here. And then it changes away according to this equation. This is a first order approximation, but with this formulation we now have the capability to calculate, given the metallicity and density of a star forming cloud, we can calculate the IMF it will produce. And in fact you can then see that at a solar metallicity, fully sampled mass functions, the cloud is so massive that it actually can make up to 100 solar masses of stars. Most massive star 100 solar masses would be the canonical mass function, and at the lower metallicity it becomes top heavy but bottom light. And at the higher metallicity we don't know what happens because we don't have data, so we just keep it at this slope at the high mass end, but it becomes bottom heavy. So more metal-rich gas fragments to make more low mass stars. That's what this means. And so now we have, so thus there's good and independent quantifiable evidence for the IMF becoming top heavy with increasing density and decreasing metallicity. Note, extraction of this evidence requires understanding of the data and of the dynamical evolution of these correlated star formation events. I mean, people who are trying to study the IMF without understanding the dynamics of these systems will never get at the correct result. I'm particularly emphasizing this because there's quite a fraction of the community who makes claims about the IMF who have never actually touched the dynamics of these systems. So the dynamics is extremely important, which is why I spend a lot of time learning how stellar dynamics works in these collisional systems. And now we can make a whole galaxy because we've got basically all the elements. So here's now a very simple argument. Imagine you have a galaxy, and at a time delta t, with a star formation rate, we build up this mass in stars. Yeah, so star formation rate times delta t makes this mass in stars. It's very simple, elementary. This total mass in stars is distributed over the star clusters which are forming in the galaxy, according to this integral from minimum smallest cluster to most massive cluster. We know that the smallest cluster which is forming is something like Taurus Auriga, say 5 solar masses. That's the smallest embedded cluster which is forming, about 5 solar masses. So that's this end here. We have one most massive cluster. Between the most massive cluster and possibly some physical limit, we take that to be something like 10 million solar masses. It could also be 100 million. This is simply not important here, but we can do the same trick. We calculate one most massive cluster in this system. Then from this and that combination, total mass here and the star formation rate, and solving these equations, we find that there's an MECL max star formation rate correlation. A galaxy with a high star formation rate is making clusters from this lowest mass cluster up until a massive cluster, which is massive, and a galaxy with a low star formation rate is making clusters from a low mass up until a most massive cluster, which is not as massive. That's what this means. Okay, so we can, what is delta t? That's a parameter. We have independent evidence. So the galaxy-wide timescale of transforming the interstellar medium via molecular clouds into a new stellar population and the disappearance of large molecular clouds around young star clusters implies delta T about 10 million years. That's the timescale that the interstellar medium makes a molecular cloud, and the molecular cloud makes new stars, and the cloud is destroyed, approximately. Yeah? So we can now solve these equations. Again, this one and that one. So this here depends on the star formation rate. That's just the mass in star clusters forming in time delta T, and there is one cluster which is one most massive cluster, and we get this correlation. Most massive cluster in a galaxy is a function of star formation rate. So here we have a galaxy with a star formation rate of 1 solar mass per year, and that would be making star clusters up until a few times 10 to the 5 solar masses. And a galaxy with a very high star formation rate would be making more massive clusters, and a galaxy with a low star formation rate would be making clusters which are not as massive. What do the data look like? That's what they look like. Yeah? So each point is now a whole galaxy with a star formation rate and a measured most massive cluster. Again, you see the same argument. You see the scatter. The scatter is too small to be consistent with random sampling. You see how big the uncertainties are. If you take out the uncertainties, the scatter is actually remarkably small. And this curve here is the one with delta T equal to 10 million years. It's remarkable how well it describes these data here. Okay. The true spread is smaller because of the substantial measurement uncertainties. So we can now create the IMF of a whole galaxy, and our exercise is actually simple. All you do is you add up all IMFs in all embedded clusters. It's the Lego principle. You have a galaxy, and each cluster is contributing an IMF according to the rules discussed. So all you do is you integrate over the whole galaxy. That's the integral from the most lowest mass cluster up until the most massive cluster, which depends on the star formation of the galaxy. This IMF is contributed by clusters of this mass, and there are this number of clusters in the galaxy. So this number of clusters are being formed, and they contribute this IMF, and then we have to just integrate over all these clusters in times of delta T. So basically the IGIMF is the integrated galactic initial mass function, the sum of IMFs in all embedded clusters. And this, if you do this, and then you calculate the chemical evolution of galaxies, the blue band magnitude of dwarf galaxies, the star formation efficiency of dwarf galaxies, and so on, it's incredible how basically all problems just disappear. It's most amazing, and there's a large literature which we've published on this. So natural explanation of the mass metal installation of galaxies and many other problems in understanding galaxies just vanish. So why is the IGMF different to the IMF? It's very simple. Imagine you have a galaxy which is making star clusters. So there are many low mass clusters, and each cluster is contributing this stellar IMF from about 0.1 solar masses up until a certain stellar mass which is not very high, like 1 solar mass or so. then there are clusters, very massive clusters, which are contributing massive stars, but they are rare massive clusters, and they can contribute a top-heavy IMF. And so the IGIMF is steeper than the IMF in each individual cluster, subject to this condition here. So we can now actually do the calculations properly, and that's the result. There's the number of stars in a galaxy forming in 10 million year intervals as a function of stellar mass. You can see this is the canonical form here. This is salpeter slope. The metallicity variation has been ignored here at the low mass end. That's something I now want to work on because of talking to Alejandro on this issue. I think this is actually very interesting to see how the metallicity variation might affect these calculations. But you can see is that a galaxy with a low star formation, like 10 to the minus 3 solar masses per year, will have a galaxy-wide IMF, which is deficit in massive stars. And a galaxy with a high star formation, like 1,000 solar masses per year, has an IMF which is now top-heavy. Yeah, and that's really remarkable, I think. It immediately resolves the discrepancy for massive stars between the salpeter index found for individual cluster and OB associations and the Scarlo index found for the Milky Way disk. For a long time I've been ignoring this problem because I could not find a solution. It just drops out with the IGIMF. The Milky Way disk has a somewhat steeper IMF than in individual clusters, which explains why Scarlo found a somewhat steeper IMF. Coming back to this Gunavartana et al. Result, remember how the galaxies with a high star formation have a top-heavy IMF, as also confirming the results of previous studies. The IGIMF predicts this correlation here. So we have here at low mass star formation rates the slope of the IMF being very steep. This is salpeter here. So this is very steep, and here at the high star formation rate we have a top-heavy form. That point is this point here, and this point is that point there. So this curve matches this curve here, goes through there. And the work by Janice Lee on dwarf galaxies is exactly this curve here. I mean, this is a prediction from the IGIMF theory which we did, then confirmed by Lee et al. With her data. This is not fitting these data. And so the implication for elliptical galaxies is that if ellipticals formed with a star-forming burst very quickly in the early universe, they would have had the top-heavy IMF overall, subject to the issue that as the massive stars are contributing the metals, this is what we discussed, the IMF at the low mass end will be shifting towards a top-heavy, bottom-heavy form as discussed. So this is where I'm very excited now, because I think possibly we might be able to actually account for what we are deducing from what you are deducing from elliptical galaxies since many years actually, within this framework, without actually having adjusted this framework to fit ellipticals. That's the important thing. Yeah? The IGIMF theory is not tweaked to fit the elliptical galaxies. And furthermore, and this is what I want to emphasize, this result here confirms what Mathieu had already deduced a long time ago, and this I find most remarkable. For a long time, again, I've been ignoring her work. I'm not ignoring, but I didn't know how to connect it, because she was arguing from the chemical properties of elliptical galaxies, and she already made a very strong statement. She said, ellipticals must have formed with a top-heavy IMF to get the metals and the alpha enrichment histories. And I think this is most remarkable. I think what she was doing was absolutely right, and I think this is really, she really deserves a lot of credit for this, by having discovered this issue decades in advance of anybody else actually catching up to that, to the argument. So I'm coming now to the end. This is just the final argument, just to remind you of this Kennicut star formation rate relation which we had here, where star formation is proportional to H alpha luminosity. That of course is wrong. You can't use this to infer star formations of dwarf galaxies. In fact, we did these calculations. So this is now the star formation as a function of H alpha luminosity. That's the linear relation by Kennicut. And for dwarf galaxies, we have this curve. This is the IGIMF result. And what we are seeing here is that the dwarf galaxies, if you measure an H alpha luminosity for dwarf galaxies, you will actually have 10 to 100 times larger star formation rates in dwarf galaxies than what you think according to Kennicut. And that entirely changes our understanding how dwarf galaxies are actually evolving, with deep implications for cosmology. And so the conclusions are that the stellar IMF is found to be surprisingly invariant up to a critical star formation density on a less than a parsec scale. Above this critical star formation rate, there's evidence for top-heavy IMF in starbursts from globular clusters and UCDs. At this critical star formation rate density, the IMF is not a probabilistic stochastic star formation distribution function. The IMF appears to be closer to an optimally sampled distribution function, which just means it's a mathematical statement to say that star formation is inherently very self-regulated. And superposition principles of the sum over all embedded clusters is a very powerful approach to quantify properties of freshly hatched stellar populations galaxies. So this leads to IGIMF. What I did not talk about is we can apply the same concepts to calculating the binary populations in whole galaxies, which we've already done. With a remarkable result here, what I think is remarkable is that dwarf galaxies should have an overall binary fraction of 80%, Milky Way is about 50%, and ellipticals about 30%. Of course, it's difficult to confirm because you'd have to resolve G-dwarf binaries in elliptical galaxies. Yeah? There's a pioneering application of this concept in self-consistent full-scale hydrodynamic simulations of galaxies by Sylvia Plöckinger et al., which she did. She invented a technique how to do this. So this is the very first incorporation of this concept into a self-consistent calculation of how a galaxy forms out of a pure gas cloud. And it's really nice to look at this paper to see how the difference with the invariant IMF. I want to thank in particular these two people here who've had a significant contribution on this whole work over time. Sver Azev, because of the stellar dynamics, I had to learn from him how to use his n-body codes. That's not a trivial affair. It meant me bringing him a lot of wine to keep him happy, and he taught me how to drive his code. And Chris Taut, of course, from whom I've learned a long time ago a huge amount concerning how to set up such populations. So thank you for listening.
Thank you, Pavel. Questions?
Hello. Well, I have a lot of them, a lot of questions, and but only just to focus. If you go to the beginning, you try to argue that the EMF is not a stochastic populated. In all your arguments, I haven't seen that you have proved it at all.
What?
You have not proved it at all. You have given some arguments, but observational evidence, there is also observational evidence that show that the initial mass function is populated stochastically. And you have not mentioned any of them at all. For example, for M33, there is all the work from Corbelli and other people that you know because you quoted in the papers, who shows that the only solution to show the stellar birth line is a stochastic populated initial mass function. Okay. So I feel a bit, I don't know, we can discuss in other place, but I only want, it's just to put a question that some of the correlation that you find, say, when you say that there is not a stochasticity, is directly a result of a stochasticity. Correlations, stochasticity produce correlations.
Well,
and
I completely disagree with that. I mean, I think Corbelli et al. Is not correct. Because, I mean, how can you arrange that the clusters systematically change in mass with radius if you have stochastic sampling? You have to have some condition to do that, right? Otherwise, you can't get that effect. I mean, we explicitly tested this. What we made is we looked at annuli with increasing radii to keep the number of clusters constant in each radius. So if you have stochastic sampling, on average, statistically, the most massive cluster should be the same and independent of radius. And this is completely excluded. So I don't see how one can keep on arguing that star formation is stochastic. And the scatter in the alpha slopes of the IMF, it's too small in observation.
No, well, my question was about this plot, if you can put it. You said that the scatter there
of the alpha values, yeah?
Yes.
Let me see if I can find it.
in that plot you are mixing a lot of different data with different number of stars for its cluster, etc. So I don't understand how do you find.
Sorry,
I don't understand your first argument.
but, it's difficult for me to get there now. Let me see if I can.
Well, we can discuss this later. The question is that you have told it like a close result, and there is evidence from other authors that show that is not so close and points to the other place. Any case,
Well, I mean,
whatever the case,
statements
we can discuss, but we will never reach a conclusion because you say, well, they are wrong. I will say you are wrong. Okay,
Well, I mean,
but any case,
well, what you have to do, if you make that statement, write a paper showing your calculations, and if it's a clean paper without mistakes.
which one?
The argument, I'm saying, if you make these statements, write a paper, publish your calculations. If the calculations are clean and without errors, the argument is accepted.
Yes.
If you have a single error, we will tear you apart.
Okay, I have showed you some of the papers showing all these things and showing, well, forget it.
Because
At some
point the field has to move forward. We can't keep 20 years in the past constantly arguing the same type of thing. Yeah, and that's, so how do you want to argue here? I mean, this is not the only argument. I never based my argument on the stochastic versus non-stochasticity only on this plot. In fact, this plot, if you look at it, has been published in 2001, I think. 2001. Since that time, I've been keeping in the back of my mind, I never argued that star formation is not stochastic based on this evidence. It's all the evidence taken together, and your challenge would be to show that this evidence, for example, M33, for example, the Mmax-MECL relation, this argument and the other arguments are wrong. This is what you would have to do if you strongly want to push for stochastic formation. And then the final answer, question you'd have to answer is, how come nature should be stochastic? What's the point of nature being stochastic? Because wherever you look, nature is incredibly self-regulated. There are always processes which counter processes.
Yes, but
so
it doesn't...
there's not even an intuitive point in having star formation being stochastic. It's a simple mathematical description. If the data are not very good, we can use the mathematical description of it being stochastic, which is what I've been doing up until a long time, because that's the simplest assumption we have. The data have clearly shown that we have to move away from this.
Let's just move the discussion for later. There are more questions here. So.
Thank you. But I found it very nice that and interesting that the IGIMF changes with the environment, and also the metallicity. Because and then my question is that do we expect a kind of change in the IGIMF radially with the galactocentric radius in galaxies?
Yes.
Because we already know that the metallicity also changes.
Exactly, yes. This is an extremely good
question.
point. So one can now apply these ideas to a local IGIMF, as we call it. So we look at, this is comparable to M33, the radial distribution of star clusters. So we look at how the IMF locally in an annulus of the galaxy changes, because the star formation density changes as a function of density. The star formation density is lower at the outer parts than in the inner parts in a self-regulated, isolated disk galaxy. And yes, the outer parts become deficient in massive stars, and this very nicely explains the UV H-alpha cutoff as opposed to the UV. So the UV, which may link to the BB stars, continues radially to a much larger distance, while the massive stars at some point they cut off, because the local star formation density is too low to be able to make star clusters which contain massive stars. So this is a prediction of the IGIMF, consequence of the IGIMF calculation. And again, I mean, you can argue for stochasticity, and I'm not against that argument, except that I think it's completely ruled out. So the point is that this would not, you cannot explain with the stochastic approach, because wherever you are, you always have an equal chance to make a massive star or not a massive star. And so the H-alpha versus UV flux will largely, given Poisson uncertainties, be independent of radius, which we do not observe in galaxies, right? And then to concoct arguments like there's a loss of photons to sort of somehow counter this. Well, one can do it, but this is simply not convincing. It has never been shown a calculation that you get exactly this result with these sort of physical processes. Yeah. Yeah.
Let's just move on.
No.
Okay, thank you for an excellent talk. And then if I can summarize, I found very interesting that you found that the mass of the cloud determines the highest mass of the star that you are able to form. And the other thing you said is that the metallicity of the cloud goes in the other side. I mean, determine how many low mass stars you form. And also this integrated star, initial mass function is also very, very interesting. However, I wonder how, I mean, the assumption behind the thing you have said, which are very reasonable, very interesting, is a sort of closed box model. In the sense that, for instance, in the nearby universe, we have M82. In M82, we know that the starburst mass, which was thought to be very big, if you take this whole thing, then you derive the upper mass of the most massive galaxy, you will have a number. But now we know that inside M82, there are hundreds of superstar clusters, which will be what you call this propagation thing. And each one of them has a mass of 10 to the 7 solar masses at maximum.
10 to the 7.
2 to the 7, yes. So there is an initial mass function of this because there are many of them. So my question is, in that case, it would imply that even, I mean, it would be a very interesting test galaxy to do what you propose, because in that case, the upper mass of the initial mass function that you should have is not the one that we assumed before, but the one that is limited by the mass of the superstellar cluster, which are in fact the star-forming mode inside this starburst. And the other thing that I had regarding the metallicity, for instance, in this case, that would be the counterpart to the high mass galaxies, a lot of metals have been thrown to the intergalactic medium because of the stellar winds. And therefore, the metallicity, which is very nice, as you said, this test that you propose should apply only for systems which are, I mean, with no interaction with the outside world.
Yes.
Yes.
So M82 is interacting quite, or was interacting quite strongly with M81. Yeah, exactly. That's a big galaxy, and it's starbursting. There's an outflow from M82. Yes. So that's not a galaxy which is itself regulated. It's been perturbed from outside quite strongly.